Now let's consider some of the reasons that we might want to go async in our program. Responsiveness. In our current blocking implementation, the entire application pauses while waiting for earthquake data to be fetched. So this can make the program feel unresponsive, especially if the network connection is slow. When you switch to async, we can prevent this blocking and allow the rest of the application to continue while wait for the data. And as a result of that, we have efficiency. When dealing with tasks that involve waiting for external resources like network requests or database queries, asynchronous programming allows us to handle multiple operations concurrently. And that means we fetch earthquake data, process other parts of our application, and even make multiple requests simultaneously. And this is the reason that we will have better overall performance. And the other thing is modern standard. Asynchronous programming now is becoming the standard approach for building network and I/O-heavy applications. By adopting async patterns in ROS, we'll be aligning with modern best practices, and we ensure that the code is well suited for handling the demands of today's software landscape. So now let's consider async and await syntax, which is the foundation for writing asynchronous code in Rust. When a function is marked with async, it becomes a special kind of a function that returns a future. This future represents a value that may not be available immediately, like the result of a network request. An async function doesn't execute its code right away. Instead, it sets up the steps to be taken to eventually produce a result. Then the wait operator that we have here. So this one is used to pause the execution of an async function until the future it returns is ready. This allows other parts of the program to run while we're waiting for the results. Once the future is ready, execution resumes and we can work with the returned value. When we combine async and await, we can write code that appears to run sequentially, but actually allows other tasks to execute while we wait for long-running operations to complete. This makes our program a little bit more responsive, maybe a lot more responsive. We could now revisit our fetch earthquake data, the synchronous one, the original one. Then we'll see that we have the request blocking get here. And in this part, the function makes a blocking network request, and it means that it holds the execution of our program's current thread until the request is completed and the response is received. While this might be acceptable in some scenarios, it can become a bottleneck when you need your program to remain responsive. And so therefore, we have the asynchronous one that we don't have the blocking here, and we'll have the async mark here. And this is a non-blocking request. So that's the main difference between asynchronous and synchronous implementation of fetch earthquake data. We can make our program a little bit more dynamic, and we can have this polling interval that every some seconds we make the request to the API. And this is the synchronous. This is a synchronous version of it. And then next we want to see the asynchronous version of it. In the synchronous one, we use, as you can see, we don't have the async and await. And also when we do the sleep on the current thread for the duration of polling interval seconds, then we use this part, which is the synchronous sleeping. In the next one, when we make it asynchronous, instead of using that thread sleep, we use Tokyo time sleep. And then we'll give it the duration. The important part is we need to adapt our earthquake data source trait and the USGS data source struct to work with asynchronous function when we switch to an asynchronous function. So in the updated code, we made two key changes. So we've got the async macro here that we use behind or before the trait. And this macro is essential when you want to define a trait that contains methods that can be asynchronous. Without it, Rust doesn't allow async methods within traits directly. And then we've got the async function here within the trait. So we have modified the fetch earthquake data method within the trait to be an async function. This means that implementations of this method, such as our USGS data source, can now use .await to pause execution. and wait for asynchronous operations like network requests to complete. Now there's only one little change left, and it is adding this Tokyo main behind the main function. And this one, or this attribute, signals to the Rust compiler that we want to use the Tokyo runtime to manage our asynchronous task. Tokyo is a very popular asynchronous runtime for Rust that provides the necessary tools and infrastructure to execute asynchronous code efficiently. An executor set up behind the scenes, the Tokyo main attribute sets up in Tokyo runtime. This runtime includes an executor which is responsible for scheduling and driving the execution of our async tasks. The executor takes care of polling future, handling task completion, and ensuring that our asynchronous code runs smoothly. And then we've got the async main function here, so we have to add this async too. And by marking it with async, we're indicating that it's now an asynchronous function itself. This means it can contain .await calls to pause execution and wait for asynchronous operations, like our fetches quick out of a real-time function to finish. And the Tokyo main attribute takes care of the complex machinery needed to run asynchronous code in Rust.